Why do we need parallel computing? Well, like socks, one can never have enough processing power. Parallel computing is necessary because, well, we may just have way too much data to compute on a single device in a reasonable amount of time. Or we may just have a reaction time, a response time that's required. Imagine if your frame rate on your video game had to be slowed down to 5 frames per second because we didn't have enough computing power. We needed parallelism. Or we might just need a backup. We might just need a way to take a machine that's executing something that's really important and have another one in parallel doing the same operation, so if something happens to the first machine, the second machine can pick up where the first one left off. Now, this particular expression or this particular law that I'm going to talk about right now is kind of falling out of favor. It may not be as relevant as it was in the 1960s whenever it was first proposed, but it still holds something of value for us in our discussion today. And it is called Amdahl's Law. Now, Amdahl's Law is a ratio. It's a speed up. So what we're looking at is how fast are we going to, what kind of a speed up are we going to experience based on a ratio of how fast one core, one processing unit can do it over how fast multiple processing units can do it. Now, it is based on 2 percentages. One is S, which is the percentage of code that has to be done sequentially. And then we have P, which is the percentage of code that we can do parallel. All right. Now, both S and P are in their percentages. It's going to be less than 1. So what we're looking at is S plus P is equal to 1, all right? Because you've got the whole 100% of the program is based in either S or P. So if one single processor takes S plus P, in other words, the amount of time it takes to execute, or excuse me, the percentage, out of the 100% of our code to execute, for a single core is S plus P. This is for a single core. What does it look like for parallel? Well, parallel, if we use the same variables, you've got S. Now, regardless of how many processors you've got, it's still going to take one processor to do the sequential code. But the parallel portion of the code can be executed much quicker. In fact, if I've got N processors, N cores, so this is N cores, executing the parallel code, then the time it takes to execute that parallel code shrinks down and shrinks down. Now, what we've got here, if we replace or substitute the S plus P with the 1, is we get the ratio that kind of defines Amdahl's Law. And so it's 1 over S plus P over N. Now, there are ways to simplify this even more so that, you know, by substituting, for example, 1 minus S for P, we can simplify it a little bit more. But I think this ratio should show us enough information about what I'm trying to bring across with Amdahl's Law. If I have just one processor, just one core, then this becomes 1 over 1. And that means that one core, we've got a speed up of 1, all right? But what happens if we say that N is equal to 3? Well, if N is equal to 3, and let's say that, let's just say that 75% of our code is parallel, and that 25% of our code is serial. Now, if we do the substitution, what we get is 1 over and 0.25 plus 0.75 divided by 3, well, this becomes 1 over 0.5, which is equal to 2. All right? Now, the this shows that with 3 processors, you'd think you'd get 3 times faster. But remember, there's this overhead, there's this portion of the code, which we're going to talk about in a second, which must be done serially. We're not going to be able to get rid of that. It has to be done sequentially. So with 3 processors, we get a speed up for a ratio of 75% parallel to 25% sequential. We get a speed up of 2. So what's the upper limit? Well, for this particular situation where I've got a parallel of 75% and a sequential of 25%, if I let n just skyrocket as high as I could, the limit as n goes to infinity, then p over n becomes 0. It drops out of our expression. And what we get is 1 over s. And so the upper limit is equal to 1 over s. In the case of our 25-75% split, that means the fastest speed up, according to Amdahl's law, that we can get is 4. All right? No matter how many processors we throw at the problem. Now, I'm not bringing up Amdahl's law necessarily so that you can compute this for every single parallel application you come up with. What I want you to talk about, or what I want you to think about, is this idea of what makes up the S bit. So let's talk about the overhead. Now, when I talk about overhead, I mean things that have to be done in order to get a parallel problem solved. This includes things like communication. Now, communication has to occur to a degree between these parallel processes. For example, if I'm trying to do some sort of analysis of a large block of data, we at least need to distribute the data out to the different components, the processing units, and then bring it all back together. That passing of information takes time in communication. We also need to do something called synchronization. Now, synchronization is important because sometimes whenever we've got this data being passed back and forth, let's say that we're doing a weather analysis. We're doing we're trying to compute or trying to predict weather. Well, we need to make sure that there's a synchronization in terms of what time we're analyzing and make sure that all the data is coordinated according to the right time. Then we've got the serial portion of our code. And the serial portion, well, this is really just the portion of the code, initializing the problem, setting up the problem, reading the data, anything that would need to be done before we can start working on the program, regardless of how many nodes that are out there. Things that are just involved in setting things up and getting things started, stuff that can't be parallelized. Then we also have the additional code needed to break up algorithm. In other words, being able to do something in parallel versus doing something in serial, there's a little bit of additional work we need to do to set up the problem. Let's talk about that large research problem where I needed to take a large data set and divide it up across all the processing units. Well, that process of breaking the code up, and then when we get all the results back from the processing units, assembling it all together, that's additional code that's needed in order to maintain this algorithm. A single processor, we're only worried about the execution of the code. But in parallel, we're also worried about the time it takes to allocate, transmit, and exchange data in order to have those different functions performed in parallel. So, we talked a little bit before about Flynn's taxonomy and the idea of the 4 classifications of parallelization. One of them was actually single instruction, single data stream, which is not really parallel. One of our classifications was multiple instruction stream, multiple data stream. otherwise known as MIMD. Now, MIMD is where what we've got is individual processing units. And the processing units, each one of them are general purpose. You just think about a single core in your computer. And each processor should be capable of of doing the complete process independently. It may just take a little bit more time. So, when you have one unit and you basically can duplicate it and have a second unit that can do exactly the same sort of process, then you've got something that's capable of multiple instruction, multiple data. Now, there are really two classifications. There's single program, multiple data, and then there is multiple program, multiple data. Some of you are looking at this thinking, this doesn't look a whole lot different than this. It's the instruction versus the program. Now, what we're looking at is with a single program, multiple data, what you've got is one overall program that is assigning code to be executed by multiple processing units. We'll talk a little bit more in detail about that when I give you some examples. But think of it as we've got one task to do. A search for extraterrestrial life. We've got one task to do, and we're going to take the code that it takes in order to process all that data, and we're going to distribute that same code out to different devices. Multiple program, multiple data, typically that's whenever different programs or different operations, maybe there's not some sort of a single operation that's being distributed out. Instead, maybe load balancing. We're doing different operations on different machines with different programs. So let's talk a little bit about the models that we're looking at whenever we're talking about multiple instruction, multiple data. Now, there are two primary classifications of the architectures of these machines. We've got something called tightly coupled, and we have loosely coupled. And the architectures, while they look similar, there are some very distinct differences between these things. So let's first talk about tightly coupled. If I've got a processor, multiple processors, so I've got a bunch of processors here, and I've got memory. And whenever I talk about memory, remember whenever we discuss memory mapping, this might also include I/O devices. And so all these devices need to communicate. How are they going to communicate? Well, they're going to communicate through some sort of interconnection network. All right, so the processors through this interconnection network are communicating with, and when I'm talking about memory, I'm talking about the kind of memory that you might see inside of your computer. Now, there are some simple characteristics about this. The interconnection network, well, that's probably going to be something like a PCB, the printed circuit board inside of your computer. So all these processors may be on a single circuit board, or maybe even closer, all of these processors may be on a single die whenever you're talking about a multi-core processor. And the processing units, each one of them has access to the memory, and the access is pretty consistent in terms of the amount of time, the hoops that have to be jumped through in order to make a connection. Each one of these processors pretty much has an equivalent, I'm kind of crossing a line here. We're actually talking about a specific architecture, but they have equivalent accessibility to each one of these devices. Now, one of the things that I didn't leave myself enough room for on here is the idea that each one of these processors also has a cache. So you're looking at some sort of local memory. I don't really know that this is going to show up very well, but you've got a cache here. So each one of these processors has a cache that it can execute code out of, giving it the ability to execute. Remember, we need to have these caches in order to improve our effective memory access time. Each one of these caches will improve the performance. Now, I didn't leave a whole lot of room over here to talk about loosely coupled, but let's just take the room we've got. What I've got is multiple processing units. Now, in this case, what I've got is each processing unit has its own local memory, and most of its execution, if not all of its execution, in terms of memory requirements, comes from its own local memory. It doesn't have access to the other processor's memories. So, where's our interconnection network? Well, in this case, our interconnection network is the one that allows us to pass messages back and forth between these processors. So, the processor's connection to other processors, its ability to communicate with other processors, typically takes the form of a network, okay, a real network. Instead of being a PCB, a printed circuit board, or being on a single die, these devices are separated physically so that they have to communicate across a network. So let's talk briefly about this tightly coupled first. Now, one of the most common implementations of a tightly coupled network is something called a symmetric multiprocessor, or SMP. This is the kind of thing that you would see with a multi-core processor. And this means that these processors typically have the same capacity, the same capabilities, the same functionality, and they also have the same time to access or the same connection to each one of the memory devices. Very symmetric. Their capabilities are very symmetric. Now, this may take the form of multi-core on a single die, or it may take the form of multiple processing CPUs on a circuit board. Their connection, the interconnection network, could be similar to a memory bus. We spoke about memory buses many episodes ago. Or it may be some sort of a central controller, or it may actually be communicating through what we call a multi-port memory. It may be that the processors themselves connect directly to the memory, and the exchange, the interconnection network itself, is the memory. Now, once again, each one of the processing units has its own high-speed cache in order to execute the code quickly and efficiently. Now, what's cool about the SMP processor? Well, it does give you an incredible improvement in performance, but only if you can do the processes in parallel. Typically, though, if we have a bottleneck with the SMP, the bottleneck is going to come in access to memory. So, and we'll talk about this in the next episode, we've got exchanges with memory into each one of the processor's caches. If I modify data inside of one of these processor's caches and another one is sharing that data, we'll talk about that in the next episode, there could be a problem. This processor either has to know that the first cache modified its data and reload it, a decrease in performance, or it'll be executing on out-of-date data and give you the wrong answer. But another advantage of the symmetric multiprocessor is that it typically takes the form of a single unit in front of you. I mean, we're all used to working on a single machine, a single computer in front of us. That uniprocessor feel is still carried over to a symmetric multiprocessor. So really, as far as the use is concerned, the parallelism is transparent to the user. It also takes less IT support because there's just one machine, one power supply, one monitor, and so forth. Takes less physical space, takes less power in order to run it too. So it's a very good way to implement on a small scale parallelism. When we talk about loosely coupled, we're looking at a slightly different configuration. Probably the most common one that you've heard is something called a cluster. Now, in a cluster, what you've got is a network, a real network, that is connecting multiple computers that are referred to as nodes. Typically, this is performed with what we call request-level parallelism. Message passing, the ability to pass messages in order to distribute tasks across the different nodes. Historically, clusters do not share any memory, but there's started to be a little bit of research in shared memory models for these clusters. Now, another requirement of clusters is the fact that, well, if you look at the tightly coupled model, there's usually an operating system, and this operating system is being run by one or, across or distributed across these processing units. A single operating system takes care of scheduling, takes care of monitoring each one of the processors. That's all done pretty much in that single unit, this whole single unit. As opposed to clusters where each one of the processing units is running its own operating system. Typically the same operating system, but each one has its own instance of its operating system. But you have to include a middleware, additional software that is going to take care, well, it operates across all the nodes, and it unifies the system as a single interface, to give it a single interface, to assign tasks, to monitor nodes, and so forth. So a slightly different arrangement in terms of the operating system too. Now, there are all sorts of applications of clusters. Typically when you're looking at tightly coupled, you're looking at just trying to speed things up to improve performance. But with loosely coupled, you have kind of larger scale things like load balancing or high availability, making sure that if a node goes down, that we've got that task taken over by another device. So there are all sorts of abilities that the loosely coupled or the cluster has that are advantages over the SMP. There are, however, consequences. One of the primary consequences is that the single operating system on a tightly coupled device gives us the ability to monitor the health of the nodes easily. The processor is the operating system is right on top of the capabilities of each one of the processors. It knows which one's alive, which one's not. It is possible to have problems monitoring the health of each one of the nodes in a cluster, or even monitoring the health of the network. So there are additional responsibilities when it comes to running a cluster. Clusters are probably going to dominate. And one of the reasons is because they are very easy to scale. To add a new node to my cluster, all I need to do is plug a new computer into the network, load the operating system, load the middleware, I'm off and running. It is also possible to create clusters from machines that didn't have any other purpose. If you've got a whole bunch of machines from your company that are being, rotated out, being replaced, the machines that are being rotated out can make a cluster, create a high performance machine just simply with used parts. It does, however, take a lot of space because you do have all of those individual machines. That said, we do have single points of failure with these tightly coupled machines. They're just one power supply, just one network interface, just one, PCB. Whereas here, you've got better redundancy. There's a power supply for each one of those. There's a network card for each one of those. So if one of them goes out, it's easier for the middleware to decide how to replace it, how to shift the responsibilities over to another node. So that's just a couple of examples of how we might implement the multiple instruction, multiple data classification of Flynn's taxonomy.